Well, you can start. Thank you very much. Good afternoon, everybody. I will present this work. This is a very basic work. What we do in this work? We are studying the splitting tensile test. How change the result of the splitting tensile test when we use different strips of metal or wood. Well, for the experimental study, we use a concrete with a characteristic strength of 45 MPa. This is the material properties, and in this figure is the size of the material, and here is where we do the samples. We use 10 samples for each configuration, and there were we use cylinders by 100 millimeter diameter and 200 millimeter height. This is the common usage in Brazil for the industry. Then we use this size of the specimens for our study. We do all the study at 28 days. Well, here I show the compressive test only for check the material properties, and then I will present the result of the splitting test with four different strips. The first one is the wood strips, that they are the standard one. And the others are with steel strips. This steel strip have a curvature equal to the specimen. Then with different sizes, 10 millimeters, 15, and 20 millimeters. Well, for do the numerical simulations, we use the lattice discrete element method. This method consists on of use a lattice, see, a 3D lattice to model the solid. Then we have a spatial discretization of the solid by a 3D lattice. All the properties of this lattice are related to the characteristic of the solid. And the time discretization is used the equilibrium formula very, very well known, and where M is the mass matrix, C is the damping matrix, F and the internal force and external applied, and we use the system of integration, explicit finite different scheme to integrate this equation. Okay, well, all the properties of the elements of the modulus of the LDEM are related with the fracture energy of the material in the constitutive law. The area of this constitutive law is related with the fracture of the material. Then this parameter, this other parameter is the critical deformation is related with the maximum force that this bar can have. Well, we use this this method in the abacus explicit. We put this using a law that is available in the abacus. This is one, and all the lattice is modeled by a 3D truth finite element, T3D2 element. And then we put all the system, all our simulations in the abacus and do in the abacus these simulations. They have more facilities. Also, we have random properties of the. We can represent the random properties of the material. How we do that? Every element has a different constitutive law. The constitutive law of the elements are related with a Weibull distribution like this. Then all the material has a random properties like this. This is very utilized when you want to simulate concrete or some or one other almost brittle material. Sorry. Well, this here is the representation of the random distributions of the properties in a cylinder and the view of them. We use a mean of fracture mechanics in this case for 146 Newton by meters, and the correlation length of 40 millimeters, and a variation, yes, of 40% of the fracture mechanics. These are the elastic modulus, and the other properties remain constant. Well, the result of the experimental analysis. The experimental analysis, we do 10 results for every one of these configurations, and we have the wooden strips resist 4.33 MPa, and the steel strips resist a little less, with 10 and 15 millimeters of size, and with the 20 millimeters of size is practically the same of the wood. Then we found that if you use the steel strips of 20 millimeters, the result is practically the same of the wooden material. This is the experimental result. We can see this here. The failure configuration is very similar when we change. The only difference is when we have steel strips for 20 millimeters, there appears some transversal fracture, more transversal fracture than in the other cases. Here appears someone, but in this case, almost always appears this transversal fracture that is not so common in this case. The numerical results, we do different models. Here is to model the concrete and the wood. And here we model the concrete, the wood, and the steel plate of the machine. And these three are the steel strips, and the results are different for the others, for the experimental. The behavior of the results of numerical result is different. Here we have for 4 MPa for wooden, and almost 6.5 for steel strips. Then the result is not so good. The final configurations are similar to the experimentals, but there is a little more, I don't know what to say, it's more linear. It's not so good, the results for the graphic configurations. When we do some 3D simulations, we can see that the cracks always start in the corners, not in the central part of the specimen, like say the theory. Then we start in the corner, and there in one corner the failure propagates to the rest of the rest of the specimen. Always we see the same problem. Well, conclusions. There is no difference on the resistance obtained between the wood strips and the 20 millimeter steel strips. This is an experimental conclusion. The failure configuration are similar, but in the steel strips appears these cross-sectional cracks. This is a problem. No, it's no problem, but this is. When we compare, are the experimental results with the simulations, the wood is very, very similar, the simulation of woods with the with the results, but the simulation of the steel strips are different and have a different behavior. We have here the experimental and here the numerical, the behavior is different. When we compare the configurations, the results are okay, but we need to disturb a little more our configurations to have a more realistic ways. Okay, this is all. Thank you very much for your attention.